Thank you very much. So, who here has heard or is familiar with Raft consensus? Decent number of people. What about Paxos? What about another consensus algorithm that's neither of the above? That's a significant reduction. So today I'm not here with a particular framework, algorithm, service or product, and I'm not here to tell you that that is the best thing. It works in all scenarios and it's better than anything else out there on the market. Instead, what I want to offer you today is an antidote to that. I want to give you a whistle-stop tour of some of the big results in distributed consensus spanning 3 decades of research, so that when you find a consensus problem in your everyday life, you know where to start when trying to tackle that. So, when people first try to take a look at distributed consensus, this is the kind of thing they see. On the left, we have part-time Parliament, Lamfort's infamous paper where he introduced the Paxos algorithm. This paper is absolutely iconic. It's a huge contribution to computer science, and it's pretty much unreadable. On the right-hand side, we have this brilliant paper from Nancy, 100 impossibility proofs for distributed computing. 100 ways to say what you want to do is impossible. That's pretty frightening. So, what is distributed consensus? The definition here is a bit abstract, I guess. It's the process of reaching agreement between a collection of machines where you're in an asynchronous setting and failures will happen. So, actual systems that you deal with. By asynchronous, we mean that there's no bound on how quickly a message will get through a network. You send a TCP packet and it's best effort. It'll get there. Hopefully, probably. But you don't get a guarantee that that's going to happen. And with machines, they'll perform a computation when they're ready, when it's scheduled. There's no guarantee or bound on how quickly that's going to happen. And the machines are unreliable. People that use the machines are unreliable. People that administer the machines are unreliable. Hard disks are unreliable. Everything's unreliable. Everything breaks. Why? Why bother with distributed consensus? Well, we've heard loads today, actually, ignoring what's on this slide, where when you want to coordinate Docker containers, how you end up using Raft or Zookeeper behind that when Kubernetes or Mesos use those. You need strong consistency guarantees sometimes. Often you don't need them for a whole system. You know, databases are very happy in their eventual consistency model and those kind of things. But for certain things like distributed lock servers, you really do need those guarantees. So let's take a walk through history. This little character, I'm going to call him Bob, and he's going to be coming along with us, and we're going to answer some basic questions. How do we reach consensus? Can we even reach consensus? What is the best method to do it, and what's going to happen in the future? We get off to a slippery start. It's 83, and it's the FLP result. This is the kind of key result that says what you're trying to do is impossible, which isn't a great way to start. So what it says is that if you have a system that's asynchronous and even one machine might fail, you can't guarantee consensus. That's huge, right? That's one machine that might fail. It doesn't even have to fail. There just has to be the possibility that it could fail. And the proof that's given for this is that on an asynchronous network, we can't tell the difference between a failed machine and a machine that is slow or a network is slow. So we might be in a setting where we believe machines have failed when they haven't because, for example, our network is suddenly much slower than it was, and then you start kicking those machines out of your system, assuming they've failed. So what do we do about this? Like many things, there's a different answer whether you're talking about in theory or in practice. In practice, we just get over it. We use timers to detect failures. We understand that if you're pinging a machine and it doesn't answer, you assume that's a failure, but maybe it's not, and that's okay. And in theory, we do these fun things like make a messages arrive within a year assumption. So we need a bound so that we can prove that eventually some stuff will happen, but we just make that bound really big, and then we'll be okay with it. So along comes the infamous Paxos. And that paper there, Part-Time Parliament, that I showed earlier on. So the problem Paxos is trying to solve is how do we reach agreement over a single value, so one-shot thing, in a scenario where failures might occur. And the approach of Paxos has these three kind of stages. Firstly, you have to have a multi-stage process to do this. You cannot just do it in a single stage. You can't just have a server say, this is the truth. Alice has the lock, or Bob has the lock. Failures might occur. Half the machines might think one thing's true, the other half might think something else is true. You must have a multi-stage process. Secondly, you need majority agreement to proceed to the next stage of the algorithm. So this means in a system of 5 nodes, you need 3 nodes to be live and participating so that you can go on to proceed. This means that you could tolerate 2 failures in a system of 5 nodes, for example. And the final one is monotonically increasing numbers. So this is the idea that when we have machines, they have clocks, and we could use timestamps, but machines and their clocks skew and can be unreliable. So we need a way of ordering things. And the way that we order things in one of the ways we can order things in distributed systems is by using values and ensuring that they increase over time, giving some notion of ordering for events. So I hesitated whether to include this, but I'm going for it. So thinking caps on for 5 minutes. Paxos. Let's do it. Right. Here we have a system of 3 nodes. We need 2 of the nodes to be up, and 1 of the nodes can fail. So we've got a majority. And there's 1, 2, and 3, and they've got a bit of state. So the first phase I'm going to call the promise phase, which is what the P is for, and the second phase I'm going to call the commit phase, which is what the C is for. So here's our friend Bob, and he would like to acquire a lock. He's asked his nearest server, that's server 3, to do this for him. So now we enter phase 1. Server 3 generates one of these monotonically increasing numbers. The number he generates is 13. And he sends a promise message out to his friends. He records that it's number 13, and these guys store 13. The conditions for when you say it's okay to a promise is if the number that you're getting is the biggest number you've seen, then you promise it. So it's all about increasing numbers here. These guys just say okay. If these guys had ever in the past promised a particular value, for example, promised Alice or Charlie a lock, they would then need to inform node 3 that this is the case. Now that we've reached the end of phase 1, node 3 is the node who is in charge. This is the master, the leader, whatever term you want to use. And node 3 can now choose what the value is going to be in this system. And the value that we're talking about here is this lock, who has it. Node 3, in this case, is free to choose whatever. So node 3 grants this lock to Bob and notifies these guys in the system. They record that Bob has a lock, and Bob is granted the lock. And all is well. That seemed like a lot of work to just tell 3 people something. So let's take a look what happens if nodes fail during this. So again, we have the same setup. Bob comes along and asks for the lock. 13 is generated. These guys say okay. Node 3 goes to tell node 1 that it's committed. And before it can carry on with what it was doing, it fails. Now, in this scenario, node 1 and node 3 have agreed that Bob will have the lock, but node 2 doesn't know what's going on. Unfortunately, here comes Alice, and Alice chooses to ask a node 2 whether she can have the lock. So node 2 enters this phase 1 where they generate a number as well. Their number is 22. The way the numbers are generated is the first digit is the highest number seen so far, and the second digit is the ID of the node. And that way you can assume that they're unique and monotonically increasing. So node 2 sends their promise to node 1. Node 1 agrees because it's the highest number they've seen, and they notify this node that Bob has the lock. So now that node 2 has finished this first phase, they are now in charge, they are now the leader. However, they've already been informed that someone has agreed to give Bob the lock. Therefore, they must also give Bob the lock and tell Alice, unfortunately, that the lock has already been granted. And this is really useful because even though the node who was in charge of doing this has failed, the information about Bob having the lock has been disseminated through the system over time, even though the person who was supposed to be in charge of this has failed. So, yeah? So, no, Bob did not get informed that he had the lock. So, with these algorithms, usually the semantics is if you get told that something's been successful, it's definitely been successful. If you don't get told, you have to ask again. So Bob would have to try one of the other guys, and they would then tell him they had the lock. But well done for noticing that. So that was Paxos. That was the original Paxos protocol, which was described in that crazy paper. Go on. So for getting the numbers, so if you generate the numbers by the first, so firstly, if you're wrong and it's not the highest number, it's okay. It's not a safety problem. You just have a failure when you try to do stage 1 and you generate a new number that's bigger than the last time you tried. To make them unique, you do have to have unique IDs associated with each machine that you can kind of append on the end to make for you to easily generate unique ones. In the static membership case, that's super straightforward. You just give them numbers when you start them up. In the dynamic membership case, that is a bit tricky, yeah. Any other questions? Paxos is a tricky one, so it's always worth discussing. So in this scenario, it took 2 round trips, in the best case, to do this work, and any node was able to go ahead and do that. And the system is up and available as long as the majority of nodes are up. So that was Laporte's original algorithm, and he went on to do more. This paper I've cited here isn't the original paper, but this paper is really, really good and really well written. So I definitely recommend Paxos made moderately complex. So Laporte's insight was that first stage wasn't at all specific to who was getting that lock. That was just one of the nodes kind of doing the work that needed to be done beforehand. They were kind of establishing themselves as being the leader, the one who was in charge. And because of that, we can do that piece of work before anybody comes along with a request, whether that's Bob wanting to acquire a lock or someone wanting to set an amount in a bank account. We can do the work beforehand, and this is where this common notion of masters and leaders, primary coordinators, comes in consensus algorithms. The great thing about this is if you do that bit of work first, now when a request comes in, it's just 1 round trip to the majority to process that request. However, that request must go to the node that is the leader. So there's got to be some extra cost paid somewhere to find out who that node is. So, we've kind of worked out how to get agreement over one value or to give one person a lock once. But how do we actually build useful systems out of this? And this is where state machine replication comes in. So we have this model that there's an application, say a key value store, and some clients who want to use the application. And what happens when the machine who's hosting the application fails? Sadness. Things break. It's not there anymore. So, the way that state machine replication works is we replicate the state of an application across multiple machines, and we have a module for consensus on the machines and on the clients, and these modules are responsible for doing that bit of work like multi-Paxos. Once agreement has been reached, the modules pass the commands up to the applications. It's important here that the consensus modules ensure that all applications see the same commands in the same order. This is just one approach, by the way. Zookeeper uses a similar-ish approach called primary backup replication. There's also other ones like chain replication. So, yay! Cap theorem. I won't say too much about this because I feel like everyone in this room probably knows about this already. It's this kind of general idea that you have to sacrifice one of consistency, availability, and partition tolerance when you want to build distributed systems. The reason that one of the cases given for this is if you have a system and it's split into two, which is a partition, and you have two conflicting requests, so Bob trying to acquire a lock and Charlie trying to acquire a lock, what do? If you ignore it, then you're not being available. If you grant the locks to both Bob and to Charlie, then you're being inconsistent. And if you're only going to grant the lock to one of them, how do you choose which to grant that to? Okay, so Paxos Made Live. This is a really, really popular paper by Google about how they use Paxos, multi-Paxos and state machine replication in Chubby. That's the same thing. And it has this amazing quote in it. There are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. In order to build a real-world system, an expert needs to use numerous ideas scattered in the literature and make several relatively small protocol extensions. The cumulative effect will be substantial, and the final system will be based on an unproven protocol. So we've done all of this work, Lamport starting his work 2 decades ago, to get to where we are. And in practice, even Google looked at this problem and went, yeah, we had to divert so much from the starting point that you couldn't prove it anyway. So, yeah. The paper's quite interesting. It covers a lot of interesting topics, such as the problem of dynamic membership and the problem of verification and transaction support. The unfortunate thing about the paper is it doesn't actually give you any solutions, really. It mostly just gives problems and vague references to how they might have solved it in the company, but it's not open source or anything like that. So, fast Paxos. This was, I think, a really, really good paper. So, we saw Paxos originally. You could ask any node to do work for you, and it would take 2 round-trip times to do that. And then we saw multi-Paxos, where you have to ask a specific node, the leader or master, and they can do it in 1 round-trip time. But what if you want both things? What if you want to ask any node and for them to be able to do it in 1 round-trip time? And that's what fast Paxos can give us. Fast Paxos uses a leader, but provides the capability to bypass the leader in most cases. The way it does this is it increases the size of the quorum. So the quorum is the number of nodes that need to be involved, so usually it's a majority, but it increases it to a larger amount, around 2/3 to 3/4, depending on how many failures you want to tolerate, and reduces the number of failures that you could tolerate. But this might be something you're willing to do in practice if you want to be able to ask any node. And you could imagine, for example, in a system operating across different data centers, that this would be super useful, because if you can just ask your nearest node instead of going all the way, to Tokyo to ask the node that happened to be the leader, this would be really useful. So, building on this, the Egalitarian Paxos. So, the basic premise of state machine replication is that every node must see the same commands in the same order. That's the thing that we've used time and time again. But the great insight of this work is that we don't actually need such strong guarantees most of the time. So on the top here, we have a set of commands that you might have to a key value store, for example. Setting a value to 1, reading the value of B, incrementing C, reading C. But in practice, you can look at this instead as a graph of ordering, and it doesn't matter whether you read B first or set C equal to 1, because the effects in the end will be the same. So in practice, there's actually tons of possible orderings, and they actually all give the same observable results. And this is the insight that was exploited by Egalitarian Paxos. So Egalitarian Paxos allows requests to be committed out of order. It assumes that there's not that many of these dependencies. If you're in a situation where there is lots of dependencies, that can be problematic. So, ViewStamp Replication Revisited. I subtitled this The Forgotten Algorithm. It was a really nice little paper. So, it's another variant of this model of getting state machine replication and using it with multi-Paxos. One of the interesting things about this paper is it uses a kind of round-robin leadership election. So those of you who are familiar with Raft are used to this idea that you do some voting to pick the person who would be best suited to be the leader. The alternative approach is to have a deterministic thing that just says, if someone died, you're the leader next. If they die, you're next. This could be faster and can be more useful in some scenarios, and other scenarios electing the most suitable leader is better. So, Raft consensus. Everyone loves Raft, that's why it's got love hearts and stuff. So, Raft has absolutely taken the community by storm. It's another variant of state machine replication and multi-Paxos that focuses on being understandable and simple, making it easier to verify and implement. The key feature of this is a very strong leadership model, a model that says that the leader is absolutely in charge. They do all the work. Everyone else is almost passive. That makes it a lot easier to reason about. And there's also a good dynamic membership support. So this is the kind of typical figure that a lot of you have probably seen before. Nodes start up in this pretty passive state, and if they don't hear from a leader, then they try to become a leader by asking for votes from other nodes and go on to be the leader. If it turns out they're out of date, they step back down again. So now we go on to one of the algorithm I'm currently working on developing. It's called IOS. And the subtitle is, Why Do Things Yourself When You Can Delegate It? So the issue with multi-Paxos, view-stem replication revisited, Raft, and a whole host of other algorithms like this is that the throughput is limited to the capacity of the leader node, the master. This guy has a lot of work to do. So when you've got a system of 3 nodes and you think, I want to tolerate some more failures, let's add some more nodes, the throughput of your system goes down. That's not scalable. So what I wanted to do with this was to look at how could we build algorithms that would be more scalable and achieve a higher throughput. IOS allows the leader to safely delegate work to other nodes in the system, allowing them to kind of take some of the load and remove some of the burden. You can ultimately reduce the job of a leader to basically just being forwarding messages to other people and checking for some failures. So that's what I'm currently working on, and that is kind of the step towards the next thing that I'm going to be working on, which is kind of my main PhD topic, which is an algorithm called Hydra. So the idea of Hydra is that at the moment we have consensus within a data center, and there's a couple of algorithms for consensus for wide area networks. But what would be really cool if we could get consensus that operates between data centers, so in geo-replicated systems. This is a really tricky problem. Common consensus algorithms do not deal well with heterogeneous latency. So the way this algorithm works is you reach agreement within data centers. Oh, actually, I have a slide on this. You reach agreement within the center. So here's Bob trying to get a lock and is asking the West Coast. They then ask the selected leaders of the other data centers. Agreement is reached within those centers, and then the result is returned. So this within the data center uses IOS. This is why I was kind of looking into this, because I was worried about the throughput. And then across data centers, it uses an algorithm that is similar to Egalitarian Paxos and fast Paxos. So we've traveled a long road. We've seen 2 impossibility results, 1 replication technique, 6 consensus algorithms, and 2 new algorithms. So I wanted to kind of begin to give you a way to reason about these different algorithms and when they might be best or most suited to different scenarios. This figure tries to approximate that by looking at the algorithms in terms of how strong is their leadership model. At the extreme end, you've got Egalitarian Paxos and Paxos. Every node is the same. You can ask any node to do work for you. It's fine. Moving along, we've got fast Paxos and Hydra. These use the model that there is a leader, but we can bypass the leader in a lot of scenarios. IOS uses this idea that there is a leader, but they can offload a bit of their work to some of the other nodes to improve throughput. We've got the standard leader-driven consensus algorithms like view-step replication revisited and multi-Paxos. And there's the real strong leadership model, which is seen in Raft. So the question is, who's the winner? Who wins the award for being the best consensus algorithm? Well, it depends on what you're looking for. If you're in a local area network, then you're wanting to be using something like multi-Paxos, Raft, or view-step replication revisited. Raft clearly wins on being understandable. Its popularity definitely shows that. I really like view-step replication revisited for its minimal latency, particularly when it's recovering from failure. For wide area networks, Egalitarian Paxos and fast Paxos have a lot to offer. Particularly if conflicts are rare, Egalitarian Paxos can do really well in terms of throughput. So, looking ahead to the future, I hope to see more algorithms giving you a compromise between this complete strong leadership model that you see in something like Raft and the there is no leader model that you would see in the original Paxos. And obviously I'm working on those. So, more understandable consensus algorithms. Understandability isn't just this kind of vague, woolly concept. It is incredibly important for safety and for proving consensus algorithms, which is in its own right an incredibly tricky topic. I want achieving consensus to be cheaper. I recently went to the Eurosys workshop on eventual consistency, and 4 speakers in a row, when they were talking about different consistency guarantees, said, oh, and there's strong consistency, but nobody uses that. Oh, and there's strong consistency, but that's too heavyweight. We don't want that. We don't talk about that. And I agree with them at half. It's pretty heavyweight. People do use it, though. People use it all the time. So I really want to see improvements on that. People here love talking about containers, microservices. No one's talking about unikernels, but I know about unikernels also, so if you want to talk to me about that, by all means do. And I'd like to see self-scaling replication. So we have this idea that we have load that goes to a system, and we scale up the system in accordance to load. But it would be really cool if we could see the same thing for failures. So as we have failures, and as the system changes, we're aware of how vulnerable we are to future failures, and the system can scale up based on its level of perceived vulnerability. This talk has missed out various things. We haven't really talked about alternative replication techniques such as chain replication and primary backup replication. We haven't talked about alternative failure models, so we've not dealt with the fact that machines could be acting maliciously. And we've not talked about alternative domains, so I've focused on machines in a data center and between data centers, but there's all sorts of interesting consensus problems, whether it's between cores on a multi-core processor or between sensor networks. So, in summary, please don't be discouraged by the abstractness and impossibility results and difficulty of consensus. Consensus is achievable and it's really useful. It's just a matter of finding the right algorithm for your problem. I'm around for the rest of the week. This is my email address. I'm also on Twitter. Please do come talk to me about consensus problems. I'm always interested to hear what you've got. Thank you.
So we got time for a few questions, if you're up for it.
Yeah, absolutely.
Any questions?
I have 2, but I need to choose now. So the interesting one first. What is does the CAP theorem? The C is for serializability, as far as I understand it, but I'm not an expert. How does that relate to consensus? Does it really forbid consensus during a partition?
So, in terms of the CAP theorem and the other impossibility results, there's a difference between having consensus in all the scenarios that you're really very likely to have, and knowing your system will be available 99.9% of the time, and the guaranteed it will always be available 100% line. So the things like the FLP and the CAP results say that we can't make this 100% guarantee. But in practice, we know that that's okay, because as long as we can have incredibly good uptime, we can deal with that. The other important thing is that it's not a safety issue. None of these results are a problem with safety. You're not going to have a lock manager that's going to hand out a lock twice. These results are about availability. So these are results about whether the system will work and whether it will give you a result, because its response to possibly not being consistent is to not be available. So if you have more than a majority of the machines fail, it will be unavailable. Even though some of your machines are still alive and they are still there, its response will be to be unavailable.
So you said in Hydra that you're using IOS for consensus within data centers. Is that a necessary thing, or would like Hydra-style consensus work even without the scalability of IOS in the data centers?
So originally I tried to have this kind of flat idea where you treated all the nodes, you used the kind of replication for between data centers just across all the nodes, and you didn't use this idea of there's using IOS within the data center. The problem is that if you do that, if you try to, for example, configure that system, it's super heterogeneous in terms of latency, and so trying to, for example, detect failures is incredibly tricky. So that's why having a separate consensus algorithm that handles the within data centers, and I happened to develop IOS just because I was looking for a real high throughput algorithm, because it would be operating underneath another algorithm. That's why that became important. I don't think that quite answered your question.
So I see that it makes sense to have two different algorithms and configurations at the different levels, but I was just wondering if it's necessary to have IOS, or it could be some other algorithm within the data.
Oh yeah, it totally could be another algorithm, and I definitely intend to write it such that I can switch out IOS and try out some other algorithms there, and have a look at what's going on. There's some really interesting work. There's an algorithm called multi-ring Paxos, which seems to be really good in terms of throughput, and I would love to compare my algorithm to something like that.
Do you auto-detect the topology between, so what is inter-data center and what is intra-data center?
That is, at the moment, just configured. When you put it, you give it that information. It's not automatically detecting that. It would be really cool if it did, though, particularly because there's not just two layers, right? There's also, whether you're using the Amazon model, you might have within the same availability zone, and things like that. So knowing that information would be really useful. Particularly just using timers to detect failures is really, really hellish, and it would be useful to have that information. That would be cool.
Any more questions? Okay. Thank you very much, Heidi.
Thank you.